There we go. Yeah, if you weren't here last time, I did record that. I just haven't loaded it yet. And sometimes I get delayed on doing that. So there's going to be a set of events that are coming off of this, and I want you to put them in an order that actually happens, starting from a place that you pick. So examples of things that could be on this order are atrial systole, atrial diastole, ventricular systole, ventricular diastole, AV valves open, AV valves shut, SL valves open, SL valves shut. And then also the words, well, with these can kind of go with these two, lub and dup, but I might have them separate on the order of the list. Like one of the things might be the sound lub happens, or atria are contracting, or ventricles are in diastole. So that set of things, the order that they go in, that's going to be a test question. There's also a test questions about like just fill in the blank stuff. Like example, if the mitral valve is open, the pulmonary valve is blank. Something like that. That kind of thing. Fill in the blank. So as an example of that, okay, mitral valve is open. That's one of the AV valves. That would have been when the atria are contracting. And if the atria are contracting, the ventricles are relaxing. If the ventricles are relaxing, the mitral valve, what order did I say this in? The pulmonary valve would be shut, that kind of thing. So the video will help with that, like kind of looking around on this circle, what things go in what order will help with that. But that's what kind of questions I use on the exam for cardiac cycle, that kind of stuff. This slide I have moved to a later lecture. So if you've got this in your packet, I'm skipping over it. This same slide is going to appear later on, either today or Monday. These next two sections I am reworking from previous years because I like how your book is organizing it. It's different from what I used to have. Okay, so we're moving on from the heart, sort of, but the heart, for the rest of the semester, you can assume that the heart is doing all these things as long as a person is alive. So it's going through cardiac cycle, it's pumping blood, and now we're going to follow blood and what happens to it going through the blood vessels. And when I started teaching this class, I saw this section, I was like, man, that's going to be boring. It is not. It was so surprising, like, wow, this is really cool. Blood vessels are not just acting like straws that carry blood all over your body, they do things. So that's where we're heading. Quiz today. The top one is the vein. Part B, capillaries are the most, or sorry, number 2, capillaries are the most permeable. And all of those things affect blood pressure. So keep doing your quizzes. We'll have those basically every day. So we're going to start with looking at structure of blood vessels and kind of how they're laid out in the body. And I really like this picture to just remind us what is the point of the blood vessels. So everything on here that's not the heart is an example of a blood vessel. And we need them to carry the blood all over the body. So the heart's pumping the blood, it's moving through the vessels. so that we're delivering oxygen and various types of nutrients, which we'll learn about in the next unit, out everywhere in the body. And at the same time, the blood is supposed to be carrying carbon dioxide and wastes from the body cells to let them leave in some way. And this is showing, we've got pulmonary circulation, which we've talked about, systemic circulation, which we have talked about, but there's a couple of things I want you to add on to this that relate to future body systems that we didn't talk about yet. And start here with renal artery, kidney, capillaries, renal vein. So we're looking at this branch right here. And I would like for you to write the word here on top of renal artery, unfiltered. The word unfiltered right here. So we've got blood coming into the kidneys, unfiltered, and then they're going to pass through capillary networks in the kidneys. And by the time they leave the kidneys, the blood leaves the kidneys and comes out the renal vein, it has been filtered. So we've kind of got lungs to do the oxygen CO2, and we've got kidneys filtering waste. And we learn all in detail about that later, but I think it's good to write it here. Filtered on this side, unfiltered on this side, filtered on this side. And then I want to look at this circulation here. That one looks different than the others. So this one is depicting, okay, we've got blood coming into the liver through the hepatic artery. Right here, see this where I'm pointing right here? Call that the celiac trunk. Right here, celiac trunk. So we've got blood coming to the liver through the hepatic artery. We've got blood coming to the stomach through the celiac trunk. And then there's another major artery called mesenteric that we didn't have you all learn that goes to intestines. And so blood is going there into the stomach and the intestines, and it's picking up nutrients. You don't have to write that, but that's where it's picking up new nutrients that you're digesting. And then the blood is moving from stomach and intestines over to the liver through something called hepatic portal vein. And in the lab, this is what you labeled as just plain hepatic vein. But it's taking blood from the stomach and the intestines, moving it over to the liver. And I want you to write right here in the liver, somewhere like around this or on top of it, nutrient adjustment. So write the word nutrient adjustment right here. Your liver is really amazing. And about half of what it does is nutrient adjustment, to take what nutrients did you just digest out of your food and turn them into the proper mix that your body needs at that time. Very cool. So we've got blood moving all over the body. The kidneys are filtering. The digestive system is absorbing. Your liver is adjusting the nutrients, and then they rejoin the bloodstream. And then we're doing the oxygen and the CO2 stuff up here. Blood vessels are essential to carry blood between all of these places. So now let's look at how they are structured. What are their layers? They've got 3 layers that can have these very formal Latin names. So the knowledge that blood vessels have 3 layers is very old. and they called them tunica for like coats. Tunica intima, tunica media, tunica externa. What I've got here for you all to write in the blue is what is that really? So tunica intima is the endothelium, which is the inner lining. It's epithelial tissue, and that'd be what the blood is touching. So here we see endothelium, or the tunica intima for artery and for vein. In the middle, there's going to be a muscle layer that you can call tunica media, or it's basically smooth muscle. And this can contract or relax, and that's going to control, is the blood vessel small diameter or is it big diameter? And then on the outside, there's connective tissue wrapping that kind of holds it all together, and there will be blood supply and nerve supply in that outer layer, the tunica externa. Blood vessels have these layers, but the amount that they have depends on what spot the blood vessel is in, let's say. But those are 3 layers. You've got epithelial lining on the inside, muscle layer, and then connective tissue on the outside. Blood vessels also are supposed to have a space inside that we call lumen. So lumen is the space. It's a void. It's an empty place. And generally, veins are going to have big lumens compared to arteries. So this is artery here. That's a picture from the old book. This is a vein here. Sometime later, as you're going back and studying, label all the tunics on both of these. You don't have to do it now. But the main reason that veins have a bigger lumen is that they've got a smaller or a thinner muscle wall. And having a big lumen helps them do their job, which we'll see later. But the veins have a thinner muscle wall, or tunica media. Artery have a thicker tunica media. So on the slide, this is the muscle, this is the muscle, and then up here, this is the muscle. So, okay, so this set of words, I'm coming back to it, I promise, kind of goes with this concept. So your blood vessels are supplying an endless loop to and from your heart, and they move in this order, starting from the heart, coming out the aorta, and eventually coming back to the heart through the vena cava. Yeah, you could put an arrow like at the end of each row, and is that what you mean, like an arrow between arterioles and capillaries? Right. Yeah. So if you read these left to right and then go down the row, so arterioles then connect to capillaries. Capillary beds connect to venules. And so on. Lots of writing. So you might put a star here on this slide and then put a star here, because they're talking about the same thing. So we've got aorta, and then we've got arteries someplace, and then they go into little arterioles, and then they go into capillary bed, then venules, then veins, then vena cava, then back to the heart. So on this list, you can have capillary beds in the systemic circulation, or you can have them in the pulmonary circulation. They're doing the connecting between aorta and vena cava. That's the general order that these circulations go through. So now we're going to look at what are the structure of these individual parts and how do they compare with the layers, these different layers of blood vessels. With arteries and arterioles, they're all having all three layers, but what the thickness of the layer is different for different ones. So when you're very close to the heart, the big arteries that are coming out of the heart, like the aorta, and let's say like the iliac arteries, which go down into the legs, and probably your carotid artery, they are known as elastic. And they have more elastic fiber running through the muscle wall because they're under high pressure. And they need to be able to stretch because the blood that just came out of the left ventricle, it's very high pressure. So these need to be able to flex a little bit, these elastic arteries. Most of the arteries in the body are considered kind of like the regular type, which we would call muscular. This is kind of the normal. They don't really flex like an elastic artery, but they can change their diameter. So they can constrict or dilate, change their diameter. And then when we get to the very smaller ones called arterioles, first, this is way smaller than these. See how this is a cell nucleus in the arteriole, and that's a cell nucleus in the muscular artery. So these are very much smaller. They don't have as much muscle. They've still got tunica externa, they've still got lining, tunica intima. But the arterioles are going to control how much blood does an organ get at a particular time. And we'll come back to that concept in a few minutes. Write the word right here in this space, shunt. Shunt, S-H-U-N-T, shunt. Shunt. Your vocab word of the day for this class is shunt. In my 8 a.m. class, it was orifice. Neither one of them, like, people go around saying that very much, but word of the day. Okay, so now we're going to look, yeah, go ahead. Shunt means to kind of direct a substance one way or the other. That's a very tacky definition. But it's controlling, this picture will help with that concept. I'm coming back to your question in a minute. There's that word, shunt. Okay. So this now we're getting close down into the very small blood vessels called capillaries. And we've got arteriole heading into this section, and it's got muscle wrappings going around it like so. And then it comes into this region that we call metarteriole. Metarteriole. And see how here there are these little muscle bands that are wrapping around the capillaries, and they can kind of open this up by relaxing, or they can close this off by squeezing narrower. And it says here, the metarteriole serves as a vascular shunt when the precapillary sphincters are closed. Like, that's a great sentence for you. Go impress your friends after this and say, did you know that metarterioles serve as a vascular shunt when precapillary sphincters are closed? Here's what this means. These little sections of blood vessel called metarteriole can help the body decide, does blood really need to go into this capillary bed, or is it needed more elsewhere? And so, like, does blood really need to go into this capillary bed right now, or is it needed more elsewhere? So should the blood go straight through here and kind of bypass this capillary bed, and take the express route back to the vein? Or should we let blood flow into this capillary bed and slow down and do some work here? So it depends on what your body needs at the moment, whether you want to have a shunt, like an express route, bypass this capillary bed, or do you want to have blood flow into the capillary bed and do a job there? So here is an example of like when your body does this. I was talking to Ty Traconis, who's my visee, and he's about to graduate, and we were talking about timing of classes. And he has biochem at 12:30, and then we're going to meet after that about his presentation. But I said, that is my least favorite time to teach, is an afternoon lecture, because everybody's sleepy. Like, you would think people get sleepy at 8 a.m., but people are usually awake at 8 a.m. Once they make it to class, let's say. But at 12:30, like if you just ate lunch and you're sitting there and the teacher's Charlie Brown like wah 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 wah, and you fall asleep. Part of the reason that you fall asleep is that you have kind of like a three-way competition in your body for blood supply and capillary supply, let's say, between your brain, your brain. You could have more blood directed to your brain. You could have more blood directed to your digestive system, or you could have more blood directed to your muscles. It depends on what you need at the moment. If you just ate and you got all these nutrients sitting in your digestive system, your body directs blood to go there, and less so to your brain. And then if you're sitting in class, less so to your muscles. So you tend to get sleepy. How many of you have had class with Dr. DeFord? You know, he's like a morning person. Like, I've never been here, even when I get here early, his Jeep's over there. And he does not eat lunch because it makes him too sleepy. So he eats a huge breakfast, like powers through all day, stays alert, even though he doesn't teach afternoon classes, but powers through. One other example. So when I was in high school, I played soccer super badly, and back then you could make the team even if you weren't good. And so I was never quite fit enough to have my brain and my muscles work at the same time, and to like think about plays and stuff. Like, oh my God, I gotta run over there, and then if I make it over there, I did not have enough like brain blood supply left to make a good decision. I was not very good soccer player because of that. So at this level, your body can decide, is this the right place for blood right now? Based on some signals from different receptors you have and so on. That's just, I think that's cool. We got some messed up, is this messed up on your pictures? It's not? Well, that's good. I won't worry about it then. So now we're going to look at, okay, we're assuming that the blood does go to a capillary. What's the capillary like? OpenStax doesn't have this equivalent of picture, and I like this one, so I use it from a different book. And I'll come back to the perfusion word in a minute, but I want us to look at, okay, let's look at how the capillary looks. So here's the lumen. This is where blood would be passing through. Here is the endothelium. It's basically one cell thick. The endothelium is basically the inside and the outside. There's no muscle here. They're very flimsy. So if you get to this level, you've got endothelium, you've got a little bit of the connective tissue around the outside, but there's basically no muscle. And that's important for capillaries to do their job. Also, capillary endothelium is not always tightly connected together, and there are these little slits or openings between the cells. It's not an accident, they're that way on purpose. So capillary walls are really thin, and it's really leaky, so that we can get transfer back and forth of wastes, nutrients, oxygen, CO2, transfer back and forth. And that's called perfusion. Perfusion is like delivery, or the exchange of materials. And it depends on capillaries being thin and leaky. This is very important to what we're going to talk about Monday. How do capillaries do perfusion is one of the Monday topics, but they basically don't have any muscle. They're just one cell worth of lining, and then they've got connective tissue around the outside. Capillaries go to every part of the body. Actually, we need to write that in this space right here. So in this space, there's an important concept to put. No body cell is very far from a capillary supply. Capillaries are supposed to be reaching very near to every single cell in the body, so we have an incredible amount of them. They got to make it to everywhere. Because the cells are depending on the capillary to bring it nutrients and oxygen and to take away its waste and its CO2. So got to be close together. This is a capillary network in an animal, not a person. What is it? You don't have one this shape.
Is it a paw?
That's close. A hoof, yeah. Good. It's a hoof, which is like kind of like a paw, kind of like a foot. This is a horse hoof capillary supply. That is so cool. So whatever part of your body, your body has a shape, and the capillary bed is basically filling up a large part of that shape. And in between all these, here comes it's got a name, I don't know it. The artery going into the hoof. That's actually the vein. This is the artery coming into the hoof. This is the vein coming back out. And you got capillary beds all through it, and they're taking the shape of the hoof because they're going close to every cell in the hoof. Hoof is alive, by the way. It's very important. This is a human class. Okay, so you got a capillary bed supplying and doing perfusion and getting close to all the cells, and then the blood has to go back toward the heart or toward the kidney or toward the stomach to pick up nutrients or drop off substances. So it's going to travel through veins to do that. Veins have a different structure than artery because the blood coming through a vein is under low pressure. We'll talk about why that is in a few minutes, but maybe this is gross, but if you've ever cut yourself and the blood comes out really fast, that's an artery. If you cut yourself and it just kind of seeps slowly, that tends to be a vein. Blood in the veins is under low pressure. Because of that, it can be hard for veins to move the blood. Excellent picture here. Are you ready? I heard that yawn. This picture's gonna be so great, it's gonna wake you up. Okay. All right, this person. If you have blood under low pressure that's trying to make it from your foot back up to your heart, or if you're sitting down and the blood is in your groin, it's trying to make it back up to the heart, it's got to go against gravity. So veins a lot of times are having to raise blood, move blood uphill against gravity. And they are specialized to do that by their structure, basically. So there's 4 big ways that blood can move through veins against gravity. And this should be a list that you memorize. 4 vein mechanisms. So first one is just that they've got a really big space. The lumen, or the space inside the vein, is big, so that makes it easy for blood to go through. Like, if I needed you all to evacuate this room and I wanted to make it easy, I would open up both the doors. Make the doors have a big lumen, so it's like easy to get through. That helps. And they will tend to have a bigger lumen than the artery right next to it. So see how much more space is in here than in the neighboring artery. So large lumens are the first mechanism. The second one is that some of your big veins in your limbs, and especially in your lower body, have valves in them. So like if you could just get the blood like that high and then it starts to fall back down, it falls back down against the vein and it's at least stuck at that level. So they help blood move one direction through your venous valves. So you would have valves basically from here down in the big veins, and then your arm veins have some valves as well. Oops, wrong way. Okay. Mechanism 3. This one is not really so much about the veins. It's about muscles pushing on the veins from the outside when our muscles contract. So a lot of your big veins run between big muscles. And you can see here some valves, and the blood has made it this far at least. And if this is a vein in my leg and it's between, say, my hamstring, my quadricep, and when I walk, the muscles are alternately squeezing and contracting around that vein, and they're pushing on the blood to push it past the next valve. This is why people that don't get physical activity, they're stuck in the hospital bed, have poor circulation because their muscles aren't helping them move blood. And if you're lying flat in the bed, like all your blood tends to pool in all your veins. So sometimes you need to help them with physical therapy. This is a big way that blood makes it back out of our legs. It's like move around, walk around, jump, run, flex, stretch, all of that. Last mechanism also doesn't really have to do with your veins. It has to do with your lungs. And it's called respiratory pump. We will have a separate 20 minutes later in the semester to talk about why this happens. But when you breathe, you end up having lower pressure in your chest cavity. And that does 2 helpful things. It sucks air in from the outside, and it also sucks blood up, or it sucks blood into the torso region. Just by having low pressure and just by breathing, you are sucking blood up from the lower body and up out of your lungs, and it's coming to this low pressure region. That's called respiratory pump. So, yeah, I don't need to talk about my bad drawing. Just know that when you breathe, it lowers the pressure, and every air, blood, everything gets sucked toward that region just because it's low pressure. That's respiratory pump. Okay. I'm going to skip over varicose veins video if you really were excited about that, go watch it on Canvas. I need to keep going to other stuff like blood pressure. Everybody kind of understands the concept of blood pressure, but to get a little deeper understanding of it, we need to define actually what it is. So by having its particular structure and by going through cardiac cycle, the heart is going to pump blood out of the ventricles under force, and it goes through a blood vessel, and it's coming in under force because the blood was squeezed by the heart. So as the blood is moving through the blood vessel, it's pushing on the walls and creating pressure on the artery walls. So what blood pressure is the force of blood pushing from the inside and putting pressure on the walls. Is that odd? Like, so I was worried, am I making this like too obvious? I'm like, well, duh, Dr. I don't know. We'll lean toward that side. So blood pressure is the highest right after it leaves the heart, right when it comes out of the aorta, and that's got to have that stretch to it to withstand the force. And then when it comes back to the heart through the veins, it's at very low pressure. This is showing you how high is the pressure at a certain spot. So first thing to look at, the unit of blood pressure is called millimeters of mercury, and that looks scary. It's just a value, like inches or liters. We measure pressure in millimeters of mercury, like that. So don't be worried about that. Higher on this scale means the blood's under higher pressure. And this is showing, okay, we just left the heart, go through aorta, elastic arteries, muscular arterioles, capillaries, blah, blah, blah. Come back to the heart. So you might draw a heart here, a little heart here. When the blood gets back to the heart through the vena cava, it is barely making it. It's very low pressure. But when it leaves the heart, it's very high pressure. One point of this is that the blood pressure falls as it moves through the system. Mm-hmm.
But when they measure blood pressure, is that like, at one point in time is that measured?
It's when we measure blood pressure, it's in the arterial system. And it's going to be in the muscular artery. So like when it's basically always around your arm, right? So it's the brachial artery blood pressure. It wouldn't have to be there, but that's just how we set up the equipment. So you're measuring at muscular artery. And notice, next thing on this graph is that when you're in the arterial system, there is a range of pressures. And there are pressure waves. So these waves, you're seeing the wave like this. The waves are coming from the cycles of ventricular systole, ventricular diastole. So your heart is pumping in time and it's creating pressure waves. So it's not a constant pressure coming through the arteries. Sometimes it's more, sometimes it's less. So it's coming in pulses or waves. And so the pressure that's associated with ventricles relaxing, we call diastolic, and we've got this coming up on the slide. The pressure associated with ventricles contracting, we call systolic. So systolic pressure, diastolic pressure.
So for diastolic, what do you want us to write? The diastolic pressure, do you want us to write relaxing under that?
You could. There's some separate slides coming up explaining these two. But the last thing I wanted to mention before we leave this is the difference between those is called pulse pressure. Pulse pressure. Pulse pressure, that difference between these two pressure values, that's really only happening in the arterial system. So I'm going to come back to that here shortly. So when we measure people's blood pressure, there are those two values that go along with these peaks and valleys in the arterial system. And the first pressure is called the systolic. The systolic is kind of like the pressure wave that's coming through, that's from ventricles contracting. So it's coming from ventricular systole, and it's going to move through your blood vessel system kind of like in a wave. That's the systolic. That pressure, we call it transient. So sometimes if people are talking about homeless individuals, they'll try to use a nicer word than homeless, and they say they're transient because they don't stay always at the same place. This is a pressure that comes and goes. It's transient. And on a blood pressure reading, it's the higher number. So we'll look at some examples of blood pressure numbers in a minute. But systolic, it comes and goes. It's the higher number. And on this, you see it's the top line in this section is a systolic. The other pressure value is diastolic. This is the pressure that happens in between contraction. So see how I'm saying here, it's the pressure in between the ventricular contractions, or you could also say the diastolic pressure is happening during the ventricular diastole, when ventricles relax. So during the time when ventricles relax, our blood pressure doesn't go to zero. There's still a residual pressure. And this is a constant, kind of a more constant number. It's always the lower number, the diastolic. Who knows their blood pressure? Like you remember your last blood pressure? Yeah, thank you. Can you share? Was it good?
I think it was like 72.
One of them was 72?
I think so, yeah.
Probably the lower number. That's a good lower number. I had a good one the last time I had a reading, but I don't remember exactly what it was.
What does it mean to have a lower, when you have a lower blood pressure?
I'll get to that in a minute. Yeah. So when we're measuring blood pressure, what we're measuring is the difference or the pulse pressure. And this is most obvious in the bigger arteries. So when we take people's pulse, we're looking at feeling the difference or detecting the difference between the systolic and the diastolic. And we do that at the big arteries. Blood pressure cuff is using brachial artery. If you see that somebody is mad and upset and their temple's throbbing, you're seeing their temporal pulse. Sometimes if you're just counting pulse on yourself and you do this, I'm not too stressed right now. It's great. Y'all are a good class. I'm checking my carotid pulse. You feel up in here. If you work in nursing and you're trying to take a pulse on a baby, you sometimes will use in their groin, their femoral pulse, or maybe behind their knee. But any of these biggish arteries around the body, you can detect pulse. Those of you going into nursing, or maybe you already know how to do this, you can take blood pressure with an old school cuff and a stethoscope, or there are also machines that do this automatically. But the way that they work is you put something that detects sound next to the artery, and then you put pressure on the cuff really high. You pump it up, you squeeze the person's arm, and then you start letting the pressure of the cuff off. So that this gray line is the cuff pressure. And when you've got the cuff on super tight, there's no blood moving through there, and there's nothing to hear. And if they're doing it to you, you're like, dang it, hurry. And they start letting the pressure off. And when they let the pressure off enough for blood to move, then there starts to be a sound. And so if you're learning to detect this with a stethoscope, the first time you hear the sound, that indicates that's the pressure that goes with their systolic. And then it'll like hiss, it goes, and you hear it. And then when the cuff gets so loose that it's not even pushing at all on the artery, you stop hearing the sounds. And so the place where you stop hearing the sounds tells you the diastolic. That's how that works. Things that can make a person's blood pressure low can be all kinds of things. I'm going to get to Abby's question. This will be the last thing of the day. Your blood pressure can be low because your heart is weak, or your blood pressure can be low because your heart is strong and your arteries are very clear. Your blood pressure can be low because you're dehydrated, or your blood pressure can be low because you're having a massive allergic reaction and you're about to die. There's all different things.
Just curious, what's the normal range?
Normal, I'll put that up here. Oh, it's on Monday, but normal is about 120 over 80, 70-ish. Yeah. So we will start on this stuff on Monday. Also bring your new notes for Monday about capillaries and blood pressure disorders. There is a worksheet. There is a worksheet in Canvas that I want you to print out and bring on Monday. It's just a black and white, simple worksheet. We'll be using that on Monday also. Good questions today.
Massive allergic reaction for this delete part is too strong.
Don't write this down yet.
Okay.
Like, that'll make more sense when we get to factors that affect blood pressure. But I just wanted to list some things for her question as a preview.